Ladies and gentlemen, this Red Gaming Tech.com video, we're going to be discussing the PlayStation 4's architecture even further. We have a lot more information regarding the buses, the CPU and GPU combination, also known, of course, as the APU, the AMD Jaguar. We have a lot more detail on the asynchronous computing and compute functionalities in general, access to the memory pools, and a lot more besides. Now, this is going to be quite a long video, and I'm most likely going to create a second video not too long into the future on what a lot of this stuff means for PC development, as it turns out, there is a lot of crossover between PC and PlayStation 4 titles. So without further ado, let's just jump in. Now, before we really start to jump into the actual architecture as a whole and really start to break this stuff down, what I want to do is just spend a few minutes to refresh people's memory on some key points. Now, I have got some videos already up on multiple things such as the AMD Jaguar, as well as the memory and so on. So if you're unsure about a specific point, do check those videos out and they will give you a lot more detail on them. If not, and you feel like I've missed something out specifically, you can always go to facebook.com/redgamingtech and you can ask for another video to be created, or I'll try and point you in the direction of an article or something that I've already done. Right, so the PlayStation 4, as many of you are aware, is running an APU design, which is basically a system on a chip. Now we'll go into that in just a moment, with of course a unified pool of 8 GB of GDDR5 memory. It is GDDR5 memory, which is specifically usually used towards graphics cards, and once again that's 8 gigs, so it's a pretty healthy chunk of memory. Now, as it turns out, the APU is a SoC design. By the way, just so we're clear on this, APU stands for Accelerated Processing Unit. Now, the purpose of this is that various assets of the CPU, the GPU, and so on are on die. That means they're all part of the same chip. Now, this is very different to on package. On package, just in case you're unfamiliar with the term, isn't actually part of the same processor. Instead, rather than it being part of the processor, it's almost part of the same module. So think of it almost like I don't know if you guys have ever seen a motherboard of a PC, but think of it like that almost. It's not exactly the same, but it's almost like a part of the same unit. It's not actually part of the CPU itself, which is very different. Rather than being part of one piece of silicon, it is a separate entity on an entire package, which is basically on chip versus on die. Hopefully I've explained that fairly well. Now, it's very important to realize that there have been numerous modifications made to the PS4's GPU and CPU combination, specifically and primarily on the GPU side of things, as it turns out. Now, one aspect that we know, of course, that is rather unique for the PS4 compared to, say, a PC, traditional PC, is, of course, the unified memory pool. Now, the unified memory pool is fairly simple. The CPU or the GPU both have access to this memory pool and can read and write separately, and can also access, more to the point, they can communicate with each other, as it turns out. And that's very important, and that's where really the power of asynchronous computing really starts to come into its own. And we'll speak about that quite a bit in a moment, but before we do that, let's talk about the GPU. So the GPU, as I'm sure many of you are aware if you've been following the PS4 development at all, or you've been doing even a little bit of Googling, know that the GPU inside the PS4 is made out of 18 GCN, also known as Graphics Core Next units. Now, these units are very similar to those in, say, the desktop GPUs of, say, the Radeon 7000 series. You can get, for example, the 7970, and they have very similar GCN units. But there are some specific differences for the PS4 version. Now, one of the primary changes, and I'm going to read you guys out a quote because I feel it's pretty succinct and does pretty much tell you everything. The original AMD GCN architecture allows for one source of graphics commands and two sources of compute commands. For PS4, we've worked with AMD to increase the limit of 64 64 sources of compute commands. The idea is that if you have a synchronous compute you want to perform, you put the commands in one of the 64 queues, and then there are multiple levels of arbitration in the hardware to determine what runs, how it runs, and when it runs, alongside the graphics that's in the system. This, by the way, is a quote from Mark Cerny. I'm sure many of you are familiar with him, of course, but he is, as you guys are probably aware, the lead architect behind the PlayStation 4. Now, I've done some reading on this, and some details are still sketchy. In other words, we still don't have full access to all of the details of the PlayStation 4. No doubt that will come in the next couple of months, but from what we do realize right now, especially from the various pieces of information on the GCN, Graphics Core Next, once again, I'm just going to say that a couple more times so you guys are familiar with the acronyms, that GCN itself was designed with some support for out-of-order processing. I'm just going to give you guys a quick tagline of what that is. You can Google some of the stuff. Sometimes I'm just going to keep stuff briefly because otherwise this video is going to get really lengthy really fast. But I probably will make other videos just to clarify some of the stuff. But apologies if I'm going to breeze over some of this. But otherwise I'm going to be here for a long time explaining some of it. But just as an overview, out of order execution or processing basically means that processor executes instructions in an order governed by the availability of the data, rather than waiting for an instruction to come along. So think of it this way. I'm just going to use a really basic example of this. By all means, you can Google for some better ones, but this is a really, really simple way. Think of it this way. Think of it that you are on an assembly line and you are packing boxes. This is a really simple example. And you can work one of two ways. One, let's say that those boxes have a number on them and you need to pack those boxes and you need to then push them along the line. Well, let's say that you're forced to work in a way that is 1 and then 2 and then 3 and then 4. So in short, people are going to give you boxes, but you have to wait for the number that is the correct order. So in other words, let's say you're on box 10, you need to wait for box 11, and then you need to wait for box 12. Now, that's obviously going to be slower than, let's say, if you were to be given box 10, and then you were to be given box, 12, and then you were to be given box 13, and then you were to be given box 11. This is a really bad example. It's very simple, but you guys get the idea. So there's a definite difference. Now, it does have some flaws and so on. I'll encourage you guys to Google this if you want more information, or you can wait for me to do a video in the next couple of days which will explain this stuff a lot better. But this is just a basic overview, just to give you guys an idea. Now, the reason it's likely that Sony have actually expanded the ability of the out-of-order processing, in other words, expanded its ability to monitor, schedule the tasks, and so on, is simple. Originally, the chip was designed to only do, 2 commands versus 64. That's an absolute massive discrepancy. That's not just a couple. And so, if they simply said, you know what, all we're going to do is we're going to just add another, 60-odd asynchronous compute engines, also known as ACEs. If we're just going to add those in with nothing else to back them up, it wouldn't really suddenly improve things. It would really make it so that, okay, well, you know what, you've got it there, but there's no actual resources available to allocate how those instructions are processed. In other words, there's no resources to tell them how it's executed, what execution resources are available. It just doesn't make sense. So there likely is some changes. Unfortunately, though, we don't really have that much information on this at the moment. Now, we know from Ubisoft, this actually gives them a lot of freedom when it comes from developing and programming and porting games from PC to PS4. Now, I'm going to go into a different video on this, probably not too long into the future, maybe in the next couple of days, but I am actually very confident that this means that we're going to get much better, much more frequent, and much more faithful versions of PC games, because, for example, Dark Souls, as I'm sure many of you guys are aware, had, I'm just going to go ahead and say, a pretty piss-poor PC port. And one of the reasons behind this is that the developers didn't really know how PC worked. Now, obviously there have been subsequent patches, and I still think the game's well worth buying, by the way, in the Steam summer sales, which are going on right now. But as it turns out, it just means that the developers didn't really know it that well. However, now they're going to be forced to learn this stuff, and indeed, Ubisoft, as well as others, are often using base versions of 64-bit Windows, and they'll be using DirectX 3D 11, so DX11. And one of the reasons, of course, they use 64-bit is because, well, memory amount. And so it's a good way to start off the development, and then they can start tweaking and porting as necessary. So now let's talk a little bit more about other aspects of the whole package, really, of the PS4. Now, what we do know about the PS4 is it does have 176 gigabytes per second of memory bandwidth. Now, this, as far as we're aware of, this hasn't been 100% confirmed, but we do know it's got 176 gigabytes per second of bandwidth. And although, as I said, the clocks and so on haven't been exactly confirmed or whatever by Sony, it's most likely that these are pretty damn accurate. We know that it's got 256-bit bus, that has been confirmed, so it doesn't really take a huge amount of math for us to figure out that it's probably got a clock speed of around 1375. I'll say that again, 1375. Now that's actually well within the range of GDDR5. Now there is still some debate on how the APU style works. However, from multiple sources now, from various interviews with game developers, various leaks and so on, we're starting to get a little bit of a clearer picture on exactly how this stuff works, and some clarifications, and finally now we are actually starting to realize that some of the previous rumors are actually true. Now, as it turns out, there are actually two buses on the PS4. Now, we know from an interview, Mark Cerny himself stated, and I quote, "We added another bus to the GPU that allows it to read directly from system memory or write directly to the system memory. As a result, if the data is being passed back and forth between the CPU and GPU is small, and you don't have issues with synchronization between them anymore, we could pass almost 20 gigabytes a second down the bus." Now, in addition to that, of course, you've got the caches on the GPUs and the CPUs. Now, the GPU level 2 cache can be simultaneously used for both graphical processing, so obviously stuff like rendering a scene, or that would be anything from textures to geometry or whatever, all the way to asynchronous computing. Of course, so that would be physics or AI or whatever else you need it to do. Now, there are, of course, issues with this. Unless some modifications were made, it would reduce basically the efficiency of the level 2 cache as well as the GPU, well, as a whole. So what Mark did, and I'm going to read you guys a quote. "We have added a bit in the tags of the cache lines. We call it the volatile bit." I'll repeat that again, the volatile bit. "You can then selectively mark all accesses by compute as volatile. When it comes time for compute to read from system memory, it can invalidate selectively the lines it uses in level 2. When it comes time to write back to the results, it can then write back selectively the lines that it uses. This innovation allows compute to use this GPU level 2 cache and perform the required operations without significantly impacting graphics operations going on at the same time. In other words, it radically reduces the overhead of running compute and graphics together on the GPU." Now, Mark himself, as well as many others on the PlayStation 4 community, have pointed out numerous times that asynchronous computing is definitely the way forward. Unlike, say, the PC, which has a ridiculous amount of power behind it, obviously, and this isn't turning into a PS4 versus PC or debate or whatever, But one of the benefits, of course, of PC is that the built-in CPU, as well as GPUs now, especially for high-end rigs, are, well, ridiculously powerful. Therefore, it hurts them less to not have to be so efficient. Now, with the PlayStation 4, that's not really the case. And so, obviously, there is a great deal of importance in not only allowing developers to be able to write efficiently, but also allowing them to modify how the game runs, how they want to program, and more to the point, giving them the tools to be able to say, you know what, this is how we want this to run, period. Now, obviously, there still are finite resources, and there have been some concerns still raised about just what happens with if a developer wants to have a lot of graphical fidelity while at the same time running a lot of compute resources. However, Mark and his team have basically engineered the PlayStation 4 to minimize this. In other words, to minimize the impact of frame rates. Right? It's that simple, because obviously you don't want the frame rates to start suffering if you're doing a lot of physics work. Now, what we do know from another video, and you guys can check this one out, feel free, from Killzone, is that we've seen the developers still only really touching, they're just dabbling with asynchronous computing and GPU computation outside of graphics. We know this. They're just saying, you know what, we're using it at the moment. I mean, Gorilla were just using it for, what was it now? Data defragmentation in the memory if memory serves, ironically. And that basically is just one of the functionalities that they're allowing. And so they're starting to really get to grips with this. Now, Sony created something by the name of Spurs, that's S-P-U-R-S. And the idea behind this was to help the PS3, funnily enough, SPUs. Now, SPUs were part, of course, of the cell processor, which powered the PS3. And the whole purpose of this was to help to get the most out of the cell's SPUs for stuff like physics and so on. However, Mark has said, and I quote, "If you look at the portion of the GPU available to compute throughout the frame, it varies drastically from instant to instant. For example, something like opaque shadow map rendering doesn't even use a pixel shader. It's entirely done by the vertex and the rasterization hardware, so graphics aren't being used most of the time. Most of the 1.8 teraflops of APU available in the CUs. Times like this during the game's frame are an opportunity to say, hey, okay, that opens up the compute you wanted to. Now turn it up to 11 now. There are some very simple controls where on the graphics side, for the graphics command buffer, you can crank up or down on the compute. The question becomes, looking at each phase of rendering and then load it places on the various GPU units, what amount and style of compute can be run efficiently during that phase. Now, as I was saying just a moment ago before I got somewhat sidetracked, there are two buses distinctly on the PS4. Now, this is very important because of the unified pool of memory, and it's a significant advantage to the PlayStation 4's architecture, primarily because the memory pool is so fast. Now, there are two buses, as I said. One of them is called Onion, the other one is called Garlic, so quite interesting names, I'm sure you'll agree. Chris Jenner, who is from Ubisoft, was recently quoted, and he was talking about how this worked. And he says, and I quote, "One's called the Onion, one's called the Garlic bus. Onion is mapped through the CPU caches. This allows the CPU to have good access to memory. Garlic bypasses the CPU caches and has very high bandwidth suitable for graphics programming, which goes straight to the GPU. It's important to think about how you're allocating your memory based on what you're going to be putting in there." Now, he himself would not, because of confidentiality agreements, and that's why a lot of this stuff is still not 100% confirmed or anything like that, but due to confidentiality agreements, he hasn't confirmed some of the stuff, but what we do know from rumors and speculation and a lot of guesswork and so on, that, well, the two buses are not being created equally. Now, what we do know is that the GPU has full access to all of the memory bandwidth available. That's 176 gigabytes per second, and this is via Garlic. However, Onion gets a significant amount less of bandwidth. Now, there have been rumors from developers, as well as various documentation, leaks, and goodness knows what else, that it's about 20 gigabytes per second, which is, well, I suppose it's considerably less, but the good news is it's more than enough. Now, what we do know of the CPU side of things is that 1 to 2 of the CPUs are allocated for the PlayStation 4's operating system and general system use. It's not 100% being confirmed yet. Most people, judging from the Killzone documentation, are assuming it's 2 CPUs for system use. That means 6 are available for games. Now, it's possible that Sony will change this. However, most people in the tech are starting to agree that it's most likely going to be 2 CPUs. As far as I'm aware, Mark or his team haven't confirmed this, but do let me know if I'm wrong there. Now, in an interview, Jenna, who once again, of course, works for Ubisoft, stated, and I quote, "The first performance problem we had was not allocating memory correctly. So the Onion bus is very good for system stuff and can be accessed by the CPU. So the Garlic is very good for rendering resources and can have a lot of data into the GPU. One issue we had is that some of the shaders allocated in Garlic, but the constant writing code actually had to read something from the shaders to understand what was meant to be writing. And because that was in Garlic memory, that was very, very slow read because it's not going through the CPU caches. That was one issue we had to sort out early on, making sure that everything is split into the correct memory regions, otherwise it can get really slow you down. Now, there's one really good thing, and that is that APIs, or application programming interfaces, for the graphics themselves are completely new. They're brand spanking new, developed specifically for the PS4. That means 2 things really, really matter here. Firstly, they're designed specifically for the PS4 hardware. That's quite important. Secondly, and probably just as importantly still, you don't have to worry about any legacy issues. You just have to worry that, look, this thing is just going to work out of the box as long as you get the settings right. Now, what we do know is that there are a couple of APIs, the first of which is named GNM. So, once again, Golf November Mother. Now, the purpose of that one, the low-level one, is to give you pretty much full, not 100% full, but pretty much full control of the GPU itself. Now, Sony themselves have actually talked about this before, but we didn't know the name. They spoke about this lower-level API back at GDC a couple of months back, but we didn't really know much about it, and we also didn't really know much about the wrapper code either, which we'll talk about in a moment as well. Now, the benefit of the GNM is that you get a lot more power and flexibility, and you can program things a lot more to your liking specifically. That means if something doesn't work quite how you want, you know what, I'm just going to change that. The negative is that you have a lot more work behind you, and it also means that you've got a lot more development time and a lot more knowledge to learn. Now, the good news is there are a lot of similarities between, say, DirectX 11 and the PlayStation 4. And indeed, this is very much like the wraparound API. Now, that's known as GNMX. So that would be Golf November Mother Xavier, as in Charles Xavier. Now, the purpose of this is it manages a lot of the details. And if you're familiar, apparently, with DX, say, 11, so that means that one of the reasons, by the way, that a lot of these indie developers are able to very quickly get their titles up and running on the PS4 is, hey, it's like DX11. Fantastic, and they can jump for joy. This is really good news because it means that they don't have to spend too long to say, oh, what's going on? You know, how do I get this working? And then have to struggle. Now, the benefit of this is ease. and just setting this damn thing up and saying, okay, you know what, this is like baby's first steps, and I don't mean that in an insulting way, I'm just saying that, look, it gives you an idea of how your code works, what does what, and there you go. Now, sometimes you'll be fine, but from reading around, other times, not so much. And other games or other projects, depending obviously how it's been developed and so on, you may need to go lower level, and mostly for things such as either memory access or whatever else. The other problem is that it actually eats up a lot more CPU, because obviously it's acting somewhat as a wrapper. So if you are using a CPU intensive application as well, that could be a problem. So it's basically a question of, do you need the extra power? Do you need the extra helping hand? If not, then you've got access to a lot more power, a lot more flexibility. It's up to you. It's a trade-off, in other words, which is pretty cool. And indeed, another area that the PS4 and the X11 have a lot of similarities is what is known as PlayStation Shader Language. And finally, the HLSL. And that's a standard in DX11. And there are small differences here and there, but they're pretty damn similar. So, as I said earlier, developers should be pretty cool. Now, the PlayStation 4, we know, has very, very good SDKs. And one of the benefits of these SDKs is it allows you to monitor things such as GPU and CPU, access, performance, bottlenecks, errors, and so on and so forth. And this is really important because, think about it, if you don't know where the error is, if you don't know what's eating up all of your GPU or CPU time and so on, you're screwed. It means you have to go through it pretty much line by line or create your own or whatever. And so, really, the purpose of Sony putting together these really, really good tools is just to allow the developers, once again, just to hit the ground running and say, okay, we can take control of this and we can go forward. Now, of course, Sony are forever going to be improving this SDK. They're forever going to be saying, okay, is there ways to improve this? Is there better ways to get better bug fixes? Is there better ways to manage, say, memory or GPU performance, and so on and so on? Now, to give you an idea of how this has actually changed over several months, there is what is known as GNMX. So that would be Golf November Mother X-Ray, once again, and that, as I said earlier, is Sony's graphics engine. Now, inside that, there's a component known as Constant Update Engine. I'll repeat that one more time. Constant Update Engine. And that handles settings, all the constants that need to go to the GPU. Constants are, well, pretty obvious when you actually read the explanation. They're basically elements like the position of a certain object. For example, the color of an object, the color of sunlight, the position on bones in skeletons, animated objects, that type of thing. Obviously, there are purposes behind this. After all, you can't animate something if you don't know where, say, the bones of the characters are. You can't render sunlight if you don't, or even the lighting of, say, areas if you don't know the constant colors of it. There are a lot more other things as well, such as, for example, if you don't know the position of an object. And so you can imagine that in modern games there's going to be, well, a lot of these constants. And so you're looking at most likely going to be hundreds in next generation titles. So the purpose here is that Sony have actually improved this, because previously it was slow and it ate CPU time up for breakfast. Now, a lot of rendering stuff, a lot of stuff that is to do with graphics generally can be very intensive. And once again, if you guys check out the Killzone analysis of this, even Guerrilla themselves, they admitted this, and more to the point, you can actually see it in the graphs that, look, this thing eats not only a lot of graphic memory, but also a lot of processing power. So if you think about it, it's almost like you guys, or any people actually, who regularly play PC games, such as myself. Now, what's the first rule of if your game doesn't work well on your hardware, and you know that it should bloody well work in your hardware? That's right, you look for a graphics driver or equivalent. So you'd update your DirectX, you'd update your graphics card drivers. So for example, you get the new GeForce drivers or new Radeon drivers or whatever you're using, and that most likely will improve the performance in the games. Now obviously, in this case, the performance difference is going to be a lot less over time because it's still fixed hardware. Whereas, for example, just to give you guys an idea, on a PC, and this is pretty generalized, but on a PC, generally developers will work on a way of getting the hardware, also a game working on a wide variety of hardware. Then it's up to AMD or NVIDIA to then improve this. Now you can actually see this from NVIDIA, for example, when AMD games are, for example, Tomb Raider, which was optimized for AMD. Now, optimized for AMD does not mean that this will not run on NVIDIA. It simply means that the developers used AMD hardware, and AMD got the title first to optimize the game better for their hardware as well. So ensure the developers optimizing for AMD, and AMD themselves have the game earlier so they can improve their driver set to better reflect that. And then, of course, NVIDIA then tried to catch up. Now, as a slight aside, the reason that NVIDIA and AMD consistently try to better put out updates, so in other words, that AMD will then release an update for a game that NVIDIA are performing better in, or vice versa, it's simple. Because they don't want to be the company that perform crap in a certain game. For example, let's say they are 20% behind on, let's just use Far Cry 3. That's not good, especially when the hardware should be pretty neck and neck. So they'll release an update because obviously, if one of your favorite games ever is, say, Far Cry, you don't want to buy the card that you're getting crappier performance on, and that's one of the reasons for that. That's a complete aside, but I just thought I'd throw that in there. Now, one issue right now that a couple of developers have actually mentioned is that the PS4's GPU is extraordinarily powerful. It really is. And there's a difference between power in terms of, T-flops and computing power, which is, obviously, the PS4 has a reasonable amount, without a question. There's a difference between that and programmable. Now, the PS4's GPU is pretty damn good, but it turns out that one of the reasons that people are saying it's very powerful is that it's extraordinarily programmable. And this is very important because this is a very important distinction to make. Now, one of the purposes here is that cross-platform games, a couple of developers have started to raise an issue because they've said, look, early on, when we're developing for the PS4, we're going to have to make sure that the game runs on both systems. So let's say you're developing a title for the Xbox One and the PlayStation 4, and you're saying, okay, well, this game needs to run on both platforms. Ignore the fact that the PS4 GPU, at least on paper, ruffle stomps on the Xbox. Sorry if you're an Xbox fan, it's just true. You guys can check this out yourselves, you can Google it, but to be honest, you probably know about this anyway. It's about 1.2 to 1.8 T-flops of computing power. Obviously 1.8 for the PS4, 1.2 for the Xbox. It's just a given. However, to be fair to Microsoft, apparently they are still trying to make final changes to the silicon. Those are the rumors. Regardless, the problem is that we do know that the PlayStation's GPU is extremely programmable. More so, at least what we assume, than the Xbox's. To be honest, though, the Xbox GPU has been a little bit more shrouded in secrecy. We do know, for example, it has the Move engines in there, which could help for some stuff anyway. But the GPU of the PS4 is going to be very programmable. The issue is that if a game is created with both systems in mind, rather than say, this game is exclusive to the PlayStation 4, it's basically going to be then down to the developers themselves to make PlayStation 4 specific changes for the rendering or for compute or whatever. Because, well, let's face it, it's a simple case of if the Xbox can't do it, they can't just have something in the code that, will work the best it can. So I guess the question that we've got to ask ourselves is just how much advantage developers will take, who are, of course, creating games for the Xbox One as well as PlayStation 4 titles specifically at the same time. I have a feeling that it's going to take a while, maybe a couple of years, before we're really able to get the answers here. One thing is definitely for sure, however. Asynchronous computing is going to become a big thing for PS4 specific titles. More to the point, the ability to run a lot more stuff on the GPU is definitely going to become a really big thing. And I have a feeling that in some areas the Xbox One is definitely going to start lagging behind. I think the PlayStation 4 is going to be easier to program for, mostly because of the way the memory pools work on the PS4. Now, finally, there is one small little thing that I should probably cover, and that would be basically the design of the APU itself. Now, as I said, the memory, or the GDDR5 memory, has 176 gigabytes per second access to the GPU, and then there's 20 gigabytes per second access on the Onion. On Garlic, as I said, it's 176, and that goes straight to the memory, and that's between the GPU and the memory. Then you've got a 20 gigabyte per second bus from the GPU to the CPU, and then finally you've got a 20 gigabyte per second bus from the memory to the CPU. So in short, the GPU, the CPU are all tied to the memory as well as tied to one another. And the purpose behind this, of course, is that means that both can read and write independently, as well as speak to one another and say, "Oh, hi, have you done this yet?" or whatever. Now, as I said, there is some points about efficiency. And the point behind this is to basically say, you know what, I can swap the data between them and so on, and it's easy. And more to the point, AMD themselves only have finite resources. Now, this is a really, really important point to make, because there are multiple finite resources when dealing with something. I've had some readers who have asked me very clinically, or very matter-of-factly, not that I blame them or anything, why haven't Sony simply said, you know what, we're just going to add in 18 GCN units and say 4 compute units, or why don't they just put in 24 compute units, or the same amount as in, say, the desktop GPUs, say 30 or 32 compute units, or why haven't they simply made the core faster or whatever. And this is pretty much exactly the same reason that I give for the Xbox. There is only a finite amount of room, there are only a finite amount of resources, and there is only a finite amount of money. So, it's a basic principle of, look, Sony can only charge a certain amount for the unit, even if they were willing to come out of pocket, which they probably are slightly, that's just a pure guess. They can't come out of pocket like, $200 or $300 per unit. That's just not feasible, and that is not a business practice, because short term they would get absolutely battered, and long term they're basically betting the entire farm to make money really quick. Therefore, there is always finite resources. So, because of this, because there are finite development resources, no system is perfect. And straight out of the box, in other words, without any improvements, there would be noticeable issues with bandwidth and latency. But, as I said, AMD and Sony have made various improvements on these areas to help iron out the issues, because of the asynchronous computing anyway. It's just a natural process. Now, Sony himself has actually commented on the purposes behind their choice of GDDR5 memory, and the whole purpose behind it was so that developers were given a lot more freedom. We know that early on the PlayStation 4's design, there were actually a couple of issues, or a couple of options. One was that they could use DDR3 memory, and they quickly threw that out. Then there was another one they had, which was GDDR5 memory, but on a smaller bus, in other words, not 256-bit. And that would give them a less memory bandwidth, but they could also offset this with ESRAM. But they said, you know what, this is not the way to go for our system, because they started to realize that yes, the maximum amount of memory bandwidth would be higher. The issue is that reality of the matter is that they didn't believe that it was what developers wanted because, well, allow me to read you guys out a quote from Mark Cerny himself. With graphics, the first bottleneck you're likely to have is memory bandwidth. Given that 10 or more textures per object will be the standard in this generation, he's talking about PS4, it's very easy to run into that bottleneck. Quite a few phases of rendering become memory bound, and beyond shifting to a lower bit per pixel textures, there's not much you can do. Our strategy has been simply to make sure that we're using a GDDR5 system memory and therefore have a lot of memory bandwidth. Now, as strategies go, it's a pretty damn simple strategy. It's the equivalent of, I don't know, something like pray and spray. In other words, you just simply, it's not very elegant in terms of a solution, but it's the best solution in this regard. As in, it hits the criteria that developers want. More to the point, it's the most efficient. It's easier to develop for. And this is one of the problems that Microsoft have had, as I've spoken about before. So it's going to be very interesting to see exactly what happens. A few developers, specifically even Gorilla, have actually mentioned that memory bandwidth is still great. It's right there. It gives them a ton of bandwidth, and it's very powerful. But they still need to be careful. And this is the point that I've made several times over. There is what is known as a lot of power, but there's also ways to use that up. And I'm going to give you guys who are PC gamers a really simple explanation for this. Let's say you buy a new GPU. The first thing you're going to do is you're going to, especially if you've been playing with an older GPU for a while, you're going to go into the graphics options and you're going to turn everything to max. And assuming you've got a good GPU upgrade, most likely that GPU will be able to play your games at max settings of whatever resolution you've, bought, especially if you had a good budget. But what happens? I remember and this is purely a personal story, I remember when I first bought a new GPU, I don't remember what it was offhand, I think it was NVIDIA's GeForce 8800. That's for pure memory. And I remember getting it home, well actually I ordered it off the internet, but whatever. And I put it into my PC, of course, after being due diligent and removing the old drivers and so forth. And I remember, first of all, cranking up the graphics settings to max, and of course, the game ran fine. But then I decided to get greedy, and so I started to really start pumping up levels of anisotropic and anti-aliasing. And so you can imagine at this point there was frame rate dips. My point being that even the highest end GPU, even the best CPU, they have limits. And so you still need to be somewhat sensible with them. As it turns out, you could buy a NVIDIA Titan, which of course is one of the best GPUs you can buy right now, and you will be paying for that privilege. But you still can pretty much render it and make it its bitch, because that's just how it rolls. Now, of course, PlayStation 4 is going to be aiming primarily at 1080p, so we're going to have to see just how long Sony can actually keep that standard up. Well, not really Sony, but games developers. You see, here's the thing. Sony themselves can't really set the standard, because they've already said, you know what, it's down to developers. And there's going to become points where, of course, 3 to 4 years' time, developers have to start making very interesting sacrifices to do with compute and graphics and everything else, because there is only a finite amount of resources for compute, a finite amount of resources for graphics, a finite amount of memory, a finite amount of CPU power. So all I'm saying is this isn't, a slur on the PS4 or whatever. I think that we're going to see really just how flexible the system is over a series of months and years, but I think I'm coming away with some very positive vibes from the PlayStation. I think that Sony have made some really good choices. I think Mark and his team have made a lot of good choices. I think some were very obvious in terms of, use GDR5 memory and so on. I don't think it was obvious in terms of the amount that they used. I think that was very cool that they used that amount. I think that the overall design of the PlayStation 4 is very efficient. I am extremely happy from a perspective of primarily a PC gamer. I do like console games, but primarily I consider myself a console gamer, a PC gamer, and so I'm very happy from that perspective because I think we're going to get much cleaner, much better ports from both ways, and this is very good for indie as well. I'm very happy about that. And I also am going to be extremely interested to see how developers use and utilize the compute functionality for titles that are multi-platform. I'm not really talking multi-platform here between PC and PlayStation 4. I'm actually discussing Xbox One and PlayStation 4 because I really think that's going to be much more interesting because PC I don't really count in this because it's got so much power behind it. They could do it any way they really want if you're talking about modern gaming PCs. Especially in 2 or 3 years' time. I don't even want to imagine how much GPU power we're going to have. A lot of GPUs now already have 3 T-flops of computing power, 2.5 to 3 T-flops of computing power. So imagine what it's going to be like in just a couple of years. We're probably going to hit the 6 T-flop barrier quite easily. In addition to that, I'm going to be very interested to see what happens in regards to the Xbox One and how it manages just to hold tooth and nail to the PlayStation. And I'm going to be very interested to see just what sacrifices, if any, the PlayStation have to make. And I'm going to be very curious on how long we can maintain that magical number of 1080p and 30 frames per second, or even better, most people want to see 1080p at 60 frames per second. And, well, we'll have to just see. It's going to be a very interesting time for everyone concerned. Now, there are quite a few topics I didn't manage to cover in this video, and I will be covering them in a series of other videos. I would have put them in this, but this has already turned into like a 50-minute by the time I've closed it out video, and you know, you guys don't realize that I've been studying. Well, this video is like 45 minutes for you, 50 minutes for you, but for me it's been about 2.5 to maybe 3.5 hours. I don't even know what it is now, recording time, in terms of research and stuff. So I need a mental break, is what it comes down to. You guys might be fine, but I'm flagging. So I'm going to have to do this over a couple of videos. There is a lot more I want to talk about. I want to talk a lot more about asynchronous computing. I want to speak a lot more about porting to the PlayStation 4. I want to speak a lot more about the Xbox One, specifically on a number of issues, and I also want to speak a lot more about PC stuff. I have a lot of really exciting things planned, so I can only hope that you guys will stick with us and join me. There will be most likely a couple of articles coming up in the next couple of days that will feature some stuff that I haven't really managed to add into this video as well, maybe footnotes and cliffs and so forth. So yeah, definitely join me for that if you have any interest to do so. Oh boy, I'm gonna go and collapse for a while because I have to record the Steam sale video in a few minutes. So yeah, anyway, while I'm in a coma, hopefully you guys have enjoyed the video. I will see you soon, hopefully, and take care, and bye for now, and well, have fun.